Hello, I'm Kunyu. Today I want to share a study in real-time energy market assassination caused by DER aggregation. Let's look at the traditional model, EP node aggregation. In the real-time market, DERs in one node can be regarded as one participant. That is the element pricing model shown in the first figure. However, power system may contain thousands of EP nodes, which means system could not solve the real-time security constraint economic dispatch in the rolling 5 minutes interval. So the system needs to simplify the bidding models and relieve the computational burden. And so far, the most popular method in practice is the commercial pricing node aggregation. It further aggregates the DERs and the nearby nodes to one participant. The aggregated bidding curve is the sum of each DER's biddings, and the aggregated power flow is calculated by shifting factor and the distribution factor, where distribution factor represents the proportion of a DER, and the shifting factor calculates its contribution to power flow. The method reduces the participant number, simplifies the system, however, loses the accuracy of power flow calculation. Because the distribution factor for an aggregator is an estimation value before the final operating, so the inaccurate distribution factor input into the market could result the system get an infeasible solution, a suboptimal solution, or oscillated solution between the two conditions, which process is illustrated in the right diagram. Therefore, we propose a network equivalent aggregation, which is expected to quickly calculate the power flow and the network constraints. Firstly, choose a connection point of aggregator and the system, as shown in the node 3 in the figure. Then project the power flows, the constraints, the bidding curves of other DERs in the aggregator to the node 3. To be clear, the equality constraints are projected by Gaussian animation, and the inequality constraints are projected by FME. After that, we can get a feasible region for the aggregator, as the shaded area shown in the figure. To generate their aggregated bidding curve, we applied the Uniject linearization structure. We're choosing a certain number of vertices to calculate the bidding references. So the bidding price at any point in the feasible region can be calculated while the weighted average of the nearby 3 vertices. In the case study, we first tested the CP node aggregation in the 4-bus system. From the right side table, we can observe the CP node aggregation results the economic dispatch oscillating between the bus 2 and bus 4 in the continuous intervals. Then we simulated the proposed network equivalent aggregation, shown in the right figure. We can see the bidding price is higher if the 923 is congested, and the aggregation performance is shown in the table. Then the difference between the proposed method and the optimal solution is smaller than 1%, when the linearization has 16 or more segments. In the 30-bus system, we added 7 sets of 5 MW DERs in the system and grouped them into 3 aggregators. We first compared the different CP node models used in practical, including the fixed distribution factor aggregation according to the DER capacitor, the updated distribution factor based on the clearing from the last interval, and the weighted average distribution factor from the past intervals. However, they all presented oscillation. Although the proposed aggregation operated in suboptimal solution, but the total cost is very close to CP node solution, and more significant than the system keeps steady without oscillation. To summarize, In this paper, we analyze the reason why CP node aggregation will cause the oscillation across multiple time intervals. To solve the issue, we proposed a network equivalent aggregation model which can effectively relieve the oscillation and achieve a feasible solution close to the optimal value. Thank you.